Hi there, welcome to my presentation for ESMARConf 2025. My name is Wolfgang Viechtbauer from Maastricht University, and I will be talking to you about how to visualize the amount of heterogeneity in forest plots. So forest plots started to appear in meta-analyses in the early 1980s, and these days they are the most commonly used visualization in meta-analyses. Why is that? Well, for one thing, they provide information about the individual studies included in a meta-analysis, but also the results of the meta-analysis itself. And they are recommended in various reporting guidelines like PRISMA, MOOS, the Journal Article Reporting Standards of the APA, and Cochran and Campbell both recommend or even require that the results of a meta-analysis are reported using a forest plot. Let's consider what is actually included in a forest plot. They are a combination of textual information and various graphical elements. They start with a study identifier, typically the first author and the publication year of the study. Then there's often summary statistics given that were used to compute the effect sizes like means, standard deviations, group sizes, or the counts of the cells in 2x2 tables to compute measures like odds ratios or risk ratios. Then we have the actual effect sizes of the studies with corresponding confidence intervals. These are typically given as points or boxes with horizontal lines corresponding to the confidence intervals. This information is also often added textually, so you can read off the numbers themselves. Sometimes the study weights are reported, so how much weight was given to each study or effect size estimate in the meta-analysis. Then at the bottom of the forest plot, we have a polygon shape, or sometimes called a diamond, and this gives the pooled estimate and its confidence interval. Then there may be information about the statistical significance of the pooled estimate and information about potential heterogeneity. That is the Q-test, maybe the I-square statistic, or the estimated variance in the true effects. And sometimes you also see that risk of bias information is added to the forest plot itself, but this is optional, of course. So let's look at an actual forest plot. This is a forest plot of the infamous meta-analysis about the BCG vaccine, which is a vaccine against tuberculosis. At the very left here, we have the study identifier, identifying the 13 trials that were included in this meta-analysis. Then we are given information needed to compute the effect sizes. Here we have counts for the number of vaccinated individuals who contracted tuberculosis or who did not, and the same thing for the control groups. Then we are shown the actual effect sizes. These are risk ratios with corresponding confidence intervals. This information is also given textually here at the very right. Then at the bottom we have the four-sided polygon or the diamond. The center here corresponds to the pooled estimate, indicating that on average vaccinated individuals had about a 50% lower infection risk than non-vaccinated individuals. The ends of this diamond correspond to the confidence interval for the pooled estimate. Then we're given information about the statistical significance of the pooled estimate and information about heterogeneity in the true effects. While information about heterogeneity is not always included in a forest plot, it's quite important to do so, because it is not only important to understand whether on average a treatment is effective or not, but also whether the effectiveness of the treatment might vary across studies. And this kind of information is captured with heterogeneity statistics, like you can see down here. However, the information that is typically reported about heterogeneity is, let's say, less than ideal. For example, the Q-test only indicates whether we can reject the null hypothesis that there is no heterogeneity, that the variance in the true effects is zero. That's important to know, but it doesn't tell us how much heterogeneity there is. The I-square statistic indicates how much out of the total variability in the observed effects is due to heterogeneity. But this is not an absolute measure of heterogeneity, because for the same amount of heterogeneity, whether we're looking at a bunch of small studies or very large studies, the I-square statistic would change. So instead, we may want to report the estimated amount of variance in the true effects. This is an absolute measure of heterogeneity, but it is kind of hard to interpret. So instead, or in addition, we may want to report a 95% prediction interval. This indicates a range where most of the true effects of similar or new studies are expected to fall, and this directly reflects the degree of heterogeneity in effect size units. The prediction interval is quite easy to compute. We take the average effect, plus and minus 1.96, times the standard deviation in the true effects, although there are various refinements to account for uncertainty in these estimates, but the principle remains the same. And this has been recommended as the best indicator of heterogeneity by various authors. Now, if we compute the prediction interval here for the BCG vaccine meta-analysis, we find bounds of 0.15 to 1.55. So this indicates that on the one hand, there may be studies where vaccinated individuals have an 85% lower infection risk. And on the other hand, there may be studies where vaccinated individuals have actually an increased risk of tuberculosis, namely a 55% higher infection risk. And this is quite a wide range, indicating that the effectiveness of the vaccine may vary a lot across studies. This raises the question how we could show the prediction interval in a forest plot. And actually various proposals for this have been made over the years, and I will show these in a second. And I want to describe two novel approaches for showing the prediction interval in a forest plot. The first proposal is to just use the same shape that we use for the pooled estimate, namely such a diamond shape, but we may want to distinguish the diamond for the prediction interval from that for the pooled estimate using color, although it still remains easy to confuse the prediction interval with the confidence interval. Alternatively, we could use a line that goes through the diamond for the pooled estimate, and the ends of that line indicate the prediction interval. But this is now easy to confuse with the confidence interval for the individual studies. And maybe this is a bit nitpicking, but we have to give the prediction interval bounds here in a different line than where visually the prediction interval is actually shown. So to clearly differentiate the prediction interval from other elements in the forest plot, we may want to use a distinguishable shape, such a horizontal bar, to indicate the prediction interval, and this has been suggested before. The problem with this is that it may suggest that every value in the prediction interval is equally likely, but this is not actually the case. In particular, values at the center of the prediction interval are much more likely than those at the extremes here, and we could indicate this using shading, where darker colors represent more likely values and these lighter shades of gray less likely values. This has not been suggested before, although Jackson suggested in another context to use shading to indicate confidence intervals. The problem with this is that it may not be clear to every reader what the shading indicates, and technically we would need a legend to be able to interpret the actual values corresponding to these shades of gray. So my suggestion would be to show actually the entire predictive distribution, because that is what we are actually estimating. We are estimating a distribution of true effects, typically assumed to be a normal distribution. And what we can use is shading to indicate certain regions of interest, like these darker shades of gray here correspond to the prediction interval. So these cut off 2.5% in the tails of that distribution at the lower and upper end. And this lighter shaded region here corresponds to the area opposite to the pooled effect. So this area here is the probability that the vaccine is not effective, which is about 11% here. We can use the same visualization to indicate differences in heterogeneity across subgroups, or maybe along a continuum for continuous predictor, or different outcomes, and I want to illustrate these possibilities now. In this forest plot, I'm distinguishing these studies that did not and that did use random assignment to the treatment versus control condition. And within each subgroup, I fitted a random effects model, estimating the average effect within each subgroup. But we can also now see whether the amount of heterogeneity differs across subgroups, and we see somewhat more heterogeneity in this subgroup compared to the other one. Let's consider a different meta-analysis, namely the one by Bangert, Drowns and colleagues, who looked at 48 studies examining the effectiveness of a particular intervention for learning. Here, the effect sizes are given as standardized mean differences, and the studies differed in their size from quite small, 16 participants, to rather large, 542 participants. Now, what I wanted to examine here is if the size of the pooled effect differs for smaller versus larger studies, but also whether the amount of heterogeneity depends on the sample size. And for this, I used a location scale model that allows me to model not only the average effect, but also the amount of heterogeneity. This forest plot shows parts of the studies that were included in this meta-analysis. We see small studies up here, medium-sized studies here, and very large studies down here. And based on the location scale model, I estimated what the average effect is for studies of size 20, 100, and 500. And also we can see how the predicted amount of heterogeneity differs across these sample sizes. So very large studies tend to be much more homogeneous than small studies. Another situation where this type of visualization may be quite useful is when we are doing a multivariate meta-analysis to analyze multiple outcomes simultaneously. For this, I want to show you the meta-analysis by Berkey and colleagues, who examined the effectiveness of surgical versus non-surgical treatment for periodontal disease. And there are two outcomes that are typically reported in studies of this type, namely the so-called probing depth and the attachment level. Without going into further details about what these outcomes actually reflect, here you see the 5 studies that were included in this meta-analysis and the observed effect sizes for these two outcomes. And using a multivariate model, we can estimate the average effect for outcome AL and PD, and we can also see how the amount of heterogeneity differs across these two outcomes using this type of visualization. So we see more heterogeneity for outcome AL. All of the examples so far have used models that assume that the distribution of true effects is a normal distribution, but this may of course not be the case. We can either assume a different distribution or estimate the distribution of true effects non-parametrically. But either way, we can use the same visualization when using these methods. And I should note that other visualizations hide the shape of the distribution, except when using shading, but shading is much more difficult to interpret than actually seeing the shape of the distribution itself. Let's go back to the meta-analysis on the BCG vaccine. Here I'm showing you again the predictive distribution assuming a normal distribution, but I also use this non-parametric method to estimate the shape of the distribution of true effects, and we can actually see that it's a sort of bimodal distribution, but the same visualization nicely shows us what that distribution looks like. To conclude, we see that the predictive distribution is visually distinct from the summary polygon or other elements in the forest plot. It clarifies that we are estimating an entire distribution of true effects, and it also shows that some values under that distribution are more or less likely. We can use shading to emphasize different regions of interest, like the tail areas corresponding to the prediction interval, and it is easily possible to create these kind of forest plots using the metafor package. Code corresponding to the examples given in this presentation can be found on my website. So here are the references for this presentation. And that's it. Thank you for watching. And any questions, comments, or suggestions are, of course, very welcome.